Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a concept of velocity potential function. So the velocity potential function actually it will be applicable only for when the fluid will be moved in the three dimensionals or three directions along with the fluid flow conditions will be like irrotational flow and incompressible flow and steady flow. So let's discuss about this one by one. So let me consider a fluid which is flowing, and suppose this is a fluid particles. Let's start this fluid particles which can move from this point, and this fluid can be moved in the x direction and also y direction and also in z direction. Okay, these three direction I have to consider. And suppose this fluid, this is the origin point. Okay, so it will be moved in the x direction, and also the fluid can move in the y direction, also it can move in the z direction. So these are the three directions are there. Okay, and along with the direction, the fluid velocity also can be changed. So what I'll do, the velocity of this fluid I'll mention here like u, and here it is v, and in the z direction let's suppose w. So these are the three velocities, three different velocities of fluid which is moving in three different directions. So similarly, if you consider this fluid, it can be also mentioned like the three different accelerations will be there. So we won't discuss acceleration part here, only will focus on the velocity potential function. Okay, so velocity, we know that what is the terms velocity, because if you want to define the velocity, we know that what is the fluid traveling in the space with respect to time. That means what is the distance traveled by the fluid with respect to time. So this is velocity definition. But what about this velocity potential function? Okay, so this velocity potential function also, it can be defined, the first thing, it is a scalar function. This velocity potential function is a scalar function. Okay, it is a function of space and time. As I told you, it is a function of space and time. Okay, it is a function of space and time, and such that its negative derivative with respect to any direction, its negative derivative with respect to any direction, x, y, z direction, okay, gives the fluid velocity in the direction, okay. That means it says that if you consider the velocity potential function, okay, and it is with respect to space and time, and its negative derivative, okay, whose negative derivative? The fluid velocity negative derivative, okay, with respect to any direction. If it goes in the x direction, if it goes in the y direction, if it goes in the z direction, all these direction velocities, okay, that negative derivative with respect to any directions gives the fluid velocity in the particular directions. Obviously, it will be same thing only, but we need to consider the negative derivative of that particular things. And this velocity potential function, actually, it is indicated by phi. Okay, so what we can write now, phi is a function of, as I told you, phi is a function of space and time. So we can write the phi equal to is a function of space. What are the space are there? Now x, y, z and time. This is function of x, y, z and t, time. So this condition will be only for unsteady flow. When the flow is unsteady, then we can consider this function. If you take the steady condition, then for the velocity potential will be, okay, for the steady condition we need to consider only function of x, y, z. There will be no time in that particular point. And similarly, as for the definition, okay, if you write the velocity, as I told you, the velocity will be considered the negative derivative of this velocity potential function. So that means the velocity in the x direction, what I can write now, u equal to minus the negative derivative, so minus of del phi. So u velocity in the which direction? That is del x. So these things we need to consider. Similarly, v equal to, we can write minus del phi with respect to dy, and similarly z equal to, I can write minus del phi with respect to UVW, this is W, with respect to del Z. So these are the velocity potential function in different, this is the velocity components in different directions. Okay, so as I told you, this is u, v and w. These are the components of velocity. These are the components of velocity in three different directions, x, y and z direction. Okay, now let's go back to our previous lectures, what we have already discussed regarding the continuity equation. So already we have seen the continuity equation for the three-dimensional, for the two-dimensional flow. So continuity equation, if you want to write for the incompressible fluid, incompressible steady state, okay, we need to consider the continuity equation for the incompressible and steady flow. Steady flow already have taken. Okay, this is for unsteady and this is for steady flow. This one. So steady flow and incompressible. Incompressible means what? The fluid cannot be able to compress. So that means there is no change in density. So density will be here constant, we can consider. These things already we have discussed regarding our types of fluid flow. You can see that video. Okay, rho is constant here. Yeah, for this, what I can write the compressible continuity equation. Continuity is very easy. Okay, let me tell you. Only you need to define the velocity with respect to directions. So I can write velocity du del u by del x plus del v by del y plus similarly del w. These are three velocities in three different directions. Okay, this is equal to 0. And now the value what we got u, v, w, let's put the values in this equation. So what we'll get? Now del with respect to del x minus of this minus of del phi by del x. Similarly, all the things we can mark it here. Del with respect to del y minus del phi divided by del y and plus similarly del with respect to del z and here minus del phi by del z equal to 0. Okay, now what we'll do, see everywhere minus term is there, negative term is there, because as per the definition negative derivative we have taken. Okay, so minus all these minus terms I'll take common and I'll keep it in the right hand side, in the 0 side. So finally what we'll get here? Now del square phi with respect by del x square. Similarly del square phi by del y square is very simple. Del square phi by del z square equal to 0. So this is the equation we have seen in the mathematics is called Laplace equation. This is the equation which we have seen in the mostly M3 mathematics 3 who are studied, maybe in that topic it is there. So this is called Laplace equation. Okay, so this Laplace equation actually, this velocity potential function will be existing when it satisfies this Laplace equation. Okay, this velocity potential function will be satisfied if they're in the Laplace equation, which will correspond, or you can say in case of any kind of fluid it should be satisfied this Laplace equation. First condition this was. Okay, now this is the Laplace equation for the three-dimensional. If you consider two-dimensional flow, then obviously this part will be not there. For the two-dimensional we can also write del square phi with respect to del x square plus del square phi by del y square equal to 0. So this is for the equation for the Laplace equation for the two-dimensional flow. Okay, now here we are talking about, like, you know, why this Laplace equation required. Okay, now this Laplace equation we got from this derivative only, and this velocity potential function will be, the flow will be possible when this condition will be satisfied. Okay, when this condition will be satisfied. This is one point. Okay, now next point. See, in this, if you see the flow velocities, or the flow is flowing in different directions. Okay, so now we need to consider the flow should be irrotational. That means we need to consider some rotational components. We need to consider some rotational components of fluid. Okay, I'll tell you the properties of this fluid in the last. So next is rotational components. So for the rotational components, we know that is omega x and omega y and omega z. These are the three different rotational components need to be considered. So omega x we can write, this is 1 by 2, this formula is there, and del w by del y minus del v by del z. Okay, this one. And omega y equal to 1 by 2 del u by this is del z y z then x, del w by del x. And similarly for the omega z we can write 1 by 2 del v by del x, and this is del u by del y. Okay, so these are the three different rotational components are there. Now if you put the value of what we got here previously in this equation 1, the value of xyz, if you put in the equation this rotational component is equation, then what we are going to get here? Now we will get first one I'll write, let's put the value of xyz from the equation 1, sorry, uvw value in this equation. So what we'll get here, let me write first. So w omega x we can write 1 by 2 bracket start del by del y minus del phi by del z and minus del by del z minus del phi by del y. So this is the equation. Now if I just take it, if I just multiply these things, what I'll get finally? Now omega x equal to, this is omega x equal to 1 by 2 square bracket start minus del square phi, we can see del y and del z, both you multiply. Now similarly here if you get, this is minus plus will be there, again del square phi divided by del y and del z, this is equation. So finally we'll get omega x equal to this one. Similarly if I want to write for the omega y that also I can write 1 by 2 directly. I'll write the value, this is minus omega square phi, so here I'll get del x del z plus del square phi divided by del x del z. Okay, and similarly I'll write for the omega z, I can write 1 by 2 bracket start, and here I can write minus del square phi del x del y. So serial it will be there, see y then z then yz, here also x then z, and here it is xy. Okay, so here also you can write zx actually, but I have written xz. So then this is delta square phi divided by delta y delta x. So everywhere same common terms are there here. So these are the three rotational components value what we got, okay, by putting the value of uvw here. Now if suppose if phi is the continuity function, if phi is continuity function, then we can write what? Del square phi by del x del y equal to del square phi divided by del y del x. You can see del square phi by del x del y, and similarly del square by del y del x. And also you can write del square phi, one more term is there, that is zx delta x delta z delta x equal to, also you can write delta square phi delta x into delta z. So similarly we can write many more we can write. Now what we'll get from this term, if you see what we can get, now we can write, so all this term, this omega x and omega y and omega z, this will be equal to z equal to 0. Okay, so now this is rotational components what you have taken. Okay, these are the rotational components. But for this, this velocity potential function, the condition is the fluid should be irrotational. Okay, so when the rotational components are 0, okay, these are the rotational components, as I told you, these are the rotational components. So the condition will be when the rotational components are 0, then the fluid is called irrotational. That means the fluid is moving in irrotational. That means we have discussed the rotational fluid and irrotational fluid. So here what we got here, the rotational components are all are 0 we got. So we can say when the rotational components are 0, then the fluid is, irrotational. And the properties of this potential function, velocity potential function will be, it can be concluded like, if the velocity potential function exists, then the flow should be irrotational. First thing, the potential function exists, then the flow should be irrotational. And second one, we can say if phi is satisfy the Laplace equation, what I told you previously. This is the Laplace equation. I told you when the fluid should be exist means it should be satisfy the Laplace equation. So we can say when the velocity potential function satisfies the Laplace equation, okay, then we can say it represents the possible steady flow, possible, steady and incompressible. Both I told possible. If it is satisfy this Laplace equation, then the fluid will be possible, steady, incompressible, okay, irrotational flow. Yeah, irrotational flow. Okay, so I hope you understand. So these are the two conditions, or you can say these are the two properties of this, this velocity potential function. And as I told you, so this is nothing, only just taken the velocity in three different directions. And the most important thing that we need to understand, when the velocity is with a function, is a scalar function and is a function of space and time, and if it is traveling, we need to consider the negative derivative of that particular velocity in that same directions. Okay, so this is all about the velocity potential function. If you're having any kind of doubt regarding this, you can give a comment on the comment box. Thank you all.